Hi, this is Xiaoshu at Lehigh University. Today we're going to go through the problems in homework 7. Now let's take a look at the first one. The first problem, it asks us to use the time and space criteria, classify the following open channel flow scenarios. Before solving this problem, let's recall the definition of the steady, unsteady, uniform, and varied flow. So at a fixed location or a specific location, if the water property, such as the water height or the flow rate, it doesn't change with time, then it's a steady flow. If it changes with time, it is an unsteady flow. At a specific time, if the water elevation, it doesn't change along the channel, it doesn't change in different location of the channel, then there is a uniform flow. If the water elevation it change, so along the channel, it's a varied flow. Now let's take a look at the scenario A. Here is a constant flow in a long prismatic channel with a mild slope. The constant flow means that the water elevation, it doesn't change with time. For instance, at point A, the water elevation at time t, it equals to the water elevation at times t plus 1. Then there is steady flow. The prismatic channel and the mild slope, it implies that the water elevation doesn't change along the channel. So it is a uniform flow. Scenario B, flow in the transition of the channel in part A to a channel with a steep slope. So similarly, the constant flow implies that the water elevation, it doesn't change with time. So it's a steady flow. The slope transit from the mild to steep. It means that the water elevation at point A and point B at time t is different. We can see it from the plot. So it's a varied flow. Scenario C, flow on a sloped parking lot during a uniform intensity rainfall event. The uniform intensity means that the intensity, it doesn't change with the time, and the rainfall intensity distribute evenly in this parking lot. And based on the rational method to calculate the peak flow rate, Q equals to CIA. C is a coefficient, I is intensity, A is an area. The C and A are the constant, and because the intensity is a uniform intensity, therefore the flow rate, it doesn't change with the time. So it is a steady flow. And because it's a sloped parking lot, the flow rate generated in point A at time t plus 1, it related to the flow rate equals to C times the intensity at time t plus 1 times A. And the flow rate generated at point B, it equals to the coefficient times the water intensity times area A, and we also need to add the water drains from other places, which is the water generated at other places at time t. Therefore, this value of these two flow rate are different. So, which means that it is a varied flow in the scenario for a sloped parking lot. Scenario D, flow on a sloped parking lot during a rainfall event that decreases in intensity over time. Similarly, because it is decreasing intensity, which means that the intensity changing with the time, therefore is an unsteady flow. And the sloped parking lot, as we just mentioned, it implies varied flow. The scenario E, flow in a prismatic channel from a rapidly opening sluice gate. Because the sluice gate is rapidly opening, which means that the water elevation at different time, it should be different. Therefore, it's an unsteady flow. And the sluice gate means that the water elevation at the upper stream and the downstream are different. So it is varied flow. Scenario F, flow during the dry season in an urban or the natural stream. The dry season implies that there is no extra flow added into the stream. Therefore, the water at a specific location, the water elevation doesn't change with the time. And the natural stream implies that the bottom of the channel is not flat. So at a specific time, the water elevation at different location should be different. Therefore, it is varied flow. Okay, let's take a look at the second problem. Channel with an unusual cross-section carries water at a flow rate of 30 cubic meters per second. The channel is made by the concrete. Therefore, based on the table 6.2, we can find the Manning's coefficient. It equals to 0.013. In this problem, it asks us to calculate the channel slope, which is denoted by S. So to calculate the slope by applying the Manning equation, first we need to calculate the hydraulic radius. The hydraulic radius, it equals to the cross-sectional area divided by the valid perimeter. The area, it equals to the area of the rectangular minus the area of the small triangular. The length of this part, it equals to 3.6 minus 1.6, it equals to 2 meters. And the length of this part, it equals to 4 minus 2, it equals to 2 meters. Because it is a right angle here, the length of the hypotenuse, it equals to 2 times the square root of 2. Therefore, the area of the rectangular, it equals to 3.6 times 4 minus the area of the small triangular, it equals to 1/2 times 2 times 2. It equals to 12.4 square meter. The valid perimeter equals to 3.6 plus the length of the bottom is 2 plus the hypotenuse, it equals to 2 times square root of 2 plus 1.6. Therefore, it equals to 10 meter. If we bring this value back to this equation, we can get the hydraulic radius. It equals to 12.4 divided by 10. It equals to 1.24 meter. So the next step is to calculate the slope by applying the Manning equation. The flow rate, it equals to 1 over the Manning coefficient times A times the hydraulic radius times the slope, and this is the Manning equation. This is the Manning equation for the metric unit. Because we already know the coefficient, it equals to 0.013. The area we just calculated, it equals to 12.4 cubic meter, and the hydraulic radius, it equals to 1.24 meter, and the flow rate, it equals to 30 cubic meter per second. If we bring this value back to the Manning equation, then we can get the slope. It equals to 0.000742. So this is the result for the problem 2. Now let's take a look at the last problem. Uniform flow occurs in a 20 feet wide rectangular channel with a discharge of 2,520 cubic feet per second. If the normal depth of the flow is 15 feet, what will be the new normal depth when the width of the channel expands to 30 feet? We assume that the slope and channel roughness remain constant in both channels. So to solve this problem, first we need to write down the Manning equation. The flow rate equals to 1.49 over n times the area times the hydraulic radius to the power of 2 over 3 times the slope to the power of 0.5. And because in this problem is in the English unit, therefore we need to pay attention that we need to times 1.69 in the Manning equation. Then the next step is to use the B and Y to represent the hydraulic radius, because we know that the hydraulic radius, it equals to the cross-sectional area over the valid perimeter. And because it is a rectangular channel, its area equals to the bottom length times the height. And its weighted perimeter, it equals to the bottom plus 2 height. If we bring this 3 equation back into the Manning equation, then we can get the flow rate equals to 1.49 over the Manning coefficient times the slope to the power of 0.5 times b times y to the power of 5/3 times b plus 2y to the power of minus 2/3. And the next step is for the channel in scenario 1, and this is the first scenario, and this is our second scenario. So for the channel in these 2 scenarios, because the flow rate, it doesn't change in these 2 scenarios, therefore the Q1 should equals to Q2. And because this term and the slope are the constant, then we can write down the equation b1 times y1 to the power of 5/3 times b1 plus 2y1 to the power of minus 2/3. It equals to b2 times y2 to the power of 5/3 times b2 plus 2y2 to the power of minus 2/3. After we arrange this equation, we can get b1 times y1 over b2 times y2 to the power of 5/3. It equals to b1 plus 2y1 over b2 plus 2y2 to the power of 2/3. And because we know b1, it equals to 20, and y1 is 15. b2 is 30, and y2 is our unknown. Therefore, in this equation, we only have one unknown, which is y2. Then we can calculate the y2. It equals to 10 feet. So which means that the new normal depth, it equals to 10 feet when the width of the channel expand to 30 feet. Let's move on to the problem 3. A rectangular irrigation channel carries a discharge of 50 cubic meter per second. the channel has a slope of 0.041, and the Manning coefficient it equals to 0.022. The bottom length of the channel it equals to 3 meters. In this problem, it asks us to calculate the normal depth, which is y sub m, by applying two different methods, the successive substitution and figure 6.4 on page 205. So let's solve this problem. According to table 6.1 for a rectangular cross-sectional area. The area equals to b times y. It equals to 3 meters times y is 3y. And weighted perimeter, it equals to b plus 2 times y. It equals to 3 plus 2y. Okay, let's take a look at the first method, which is the successive substitution. The Manning equation is Q equals to 1 over n times the cross-sectional area times the hydraulic radius to the power of 2 over 3 times the slope to the power of 1 over 2. We call it equation 1. And we know that the hydraulic radius, it equals to the area over the weighted perimeter. We call it the equation 2. If we bring the equation 2 to the Manning equation, we can get the flow rate equals to 1 over n times the area times the weighted perimeter times the slope. Because the flow rate, the area, and the slope are all a constant, therefore we need to arrange this equation to put the three terms on the right hand side and put the area and weighted perimeter on the left hand side. Then we can get and because in the previous step we used y to represent the area and weighted perimeter, we can bring this two equation back into this one. The area equals to 3y. The weighted perimeter equals to 3 plus 2y. And n equals to 0.022. Q equals to 50 cubic meter per second. And the slope, it equals to 0.041. So if we bring this equation and the value back into this one, we can solve the normal depth. It equals to 2 meters. Also, we can get the value of this term, the n times q times the slope to the power of minus 0.5. It equals to 5.43. We will use this term later. So this is the normal depth we calculated by applying the successive substitution method. Now let's use the second method, which is based on the figure 6.4 to determine the normal depth. So by applying the figure 6.4, first we need to calculate the value of the x-axis. It equals to n times q times k sub m to the power of minus 1 times the slope to the power of minus 0.5 times the bottom length to the power of minus 8/3. Because in the previous steps we already know the value of n times q times s, it equals to 5.43. In the metric unit, the k sub m is unit transformation coefficient. It equals to 1. And then we need to times the bottom length. It's 3 to the power of minus 8/3. And then we can get the value of this term. It equals to 0.29. So this is our first step, is to calculate the value of this term. So the next step is to read the value of normal depth over
B, the bottom left, according to the figure 6.4.
So based on the previous steps, we calculate the value of this term, which is the value of x-axis. It's close to 0.29. So the next step is to draw a vertical line when this term equals to 0.29. Then to find the intersection point with the rectangular curve. Because based on the given information, the cross-sectional area of the channel is rectangular. Then we need to draw a horizontal line to read the value of the y sub n over b. It's close to 0.63. So the next step, we can calculate the value of y sub n. It equals to 0.63 times b, and b is the length of the bottom. It equals to 3 meters. Therefore, by applying the figure 6.4, we got the normal depth. It's close to 1.89 meters.